first speaker of this session, Laurent Pujo-Menjouet from Lyon, and he will talk about neuron scale modeling of prion production with unfolded protein response. You have 40 minutes, questions included.
Okay, I will try to share my screen, and hopefully it's going to work as it was working lately. Is it okay? Do you see the full screen?
No.
Oh, it's not the full screen?
No, it's not the full.
It's the small one? Okay, hold on. Let me try again. Okay. If I share the window. Oh, I lost you. Okay. Where is it? Okay. Okay, hold on. I will. I lost my.
Yeah, we can see
my
you,
presentation. What can you see?
No, we can. We cannot see your screen. Only you.
You can only see me, but I don't know what happened. Like, okay, hold on. Okay. For some reason, it switched off my my keynote presentation, so I'm back. Okay, and I will share my window if it's working. So now, can you see it or not?
No, not yet.
Always me?
Yes, always you.
Ah, this is really strange.
Maybe, yes, you have to. Yeah. Now it's okay, but it's not full. Yes, maybe you can do. Full. No.
Okay, maybe I can do it this way. That should be the best one.
Go ahead.
I'm sorry. I'm sorry. This is going to be this way. I will send you the other way next time. I wanted to thank all the organizers for inviting me for this this conference, and I'm going to not talk about the COVID disease, but some very interesting and actually fatal disease, which is called prion. And before starting prion, I will and the study and the mathematics behind, I will just remind what is prion. And it all started with two French who found the cause of this non-conventional agent. And this was in 1936, and it was not a virus. It was not even a bacteria. And it puzzled people for a long time up to the early 1980s, where they discovered exactly what it was. And even if it was a controversy at that time, there was a huge crisis called the mad cow disease crisis that triggered the interest of this disease in the world, and more particularly in Europe, like in the United Kingdom and in France, where there were a large number of ESB, which is BSE, bovine spongiform encephalopathy, and that was a huge crisis. And the BSE gave the impact of this disease went to the human, actually, people. And you can see the damages on the brain. On the left, it was a brain damaged with a prion disease, and on the right, it's a normal brain. So the name spongiform is because the brain looks like a sponge, and this is a huge problem, and it causes the death of the patient once the symptoms are shown. In humans, it's not called the BSE. It has several names. It's called the Creutzfeldt-Jakob disease and a variant, and it's and the CRU and the GSS and the FFI, and it's located in different parts of the brain. And this is going to be the second part of my talk, the fact that it can happen in different parts of the brain. So what is exactly the prion? The prion is, as I said, is not a virus, it's not a protein, it's not a bacteria, it's a protein. And the thing is, like, how can a protein be infectious? And that is a huge problem. And that was puzzling people for a long time. And it was Prisoner in 1982 who proved that and called it the PRP, which is called prion protein cellular, and C for cellular, it's the normal form, and PRPSC for the scrappy, which is the pathologic form. And what happens is, like, the normal form, which is located on every single cells of your body, but on the membrane, suddenly, for some reasons, becomes a bad form. And you can see in the good form, you can see alpha helices, the red helices, and beta sheets, the blue sheets, and on the bad form called scrappy for the sheep disease, you see more of these beta sheets. And this form is going to enable all these proteins to just put all together and become what we call a polymer. That is going to be, these proteins are going to attach together to form a polymer. And this is this form that is going to be the one that is going to spread in the brain and cause the fatal disease in the brain of people damaged with the prion. So just to remind you that it took a long time, almost 60 years, just to discover that it was a protein and not a virus and not a bacteria. It's because the size of a protein is really, really small. And it's almost impossible to observe it with a microscope. So just to let you know, like, a cell is about this size, and a bacteria is about the same size. A virus can be much smaller, and the protein is, like, barely noticeable when you observe it. So that's why it was quite difficult to observe this disease, and then to see it was due to the to this protein. What we could see is the indirect form of this protein impact through some what we call vacuoles, which is like some holes in the brain. It's called spongiosis, again, because it looks like a sponge. And the plaques. And the plaques are like the accumulation of these proteins. So because there are like a large number of proteins, it becomes like visible on the microscope. So how, as mathematicians, do we see this kind of, how do we see this kind of let's say, this kind of disease spreading? So we decided to study this disease through only the two kinds of proteins, like the normal form, which are like these single circles, the blue circles, which are good, and they are safe for the body. But when they become pathologic, they get this red form, and they are able to accumulate and to polymerize. Polymerize means that they can attach to themselves and lengthen. So if you have like in a plane, you put on the x-axis the size and on the y-axis the quantity of proteins. Let's say with the experiment, you have a lot of monomers. You have like polymers of size 2, of size 3, of size 4, and you want just to know how you classify them. Then you have like 15 monomers. In our example, you have like 15 monomers of size 1, 4 dimers like size 2, 4 trimers of size 3, etc. And what you want to know is exactly how this cell is, these proteins are distributed with respect to size. And you have like 2 ways of doing that. It can be a discrete way, where all the size is like a discrete size, which is like size 1, size 2, size 3, size 4, etc. And you have like a discrete model with the number of elements is going to be the number of monomers called M, plus the sum here is like from 2 to 4 of the different polymers. So this is what we call the discrete approach. And there are like mathematical model with this discrete approach. But you can also imagine that the size of a polymer can be so large, like let's say like 10,000 of monomers attached together. Then the size is of one monomer is so small that we can consider it as a continuous model. So if we tend the size to 0 of a monomer, then we get, instead of this sigma, we get this integral with respect to size. X is the size, and we get a size structured model. And actually, for some reasons, like for analytical analysis of the models, it's easier to study the continuous model. And sometimes for numerical simulations, we use the discrete model. So it depends on what we wanted to study for prion. So I like this image. Like it's just like when I peel potato, it's just like very scattered. It takes me a long time. And when my mom peels potato, it's very fluid, it's very continuous. So it's always, for analytic reason, easier to study continuous model rather than discrete models. So in 1995, one researcher called Peter Lansbury Jr. Decided to study the model with an hypothesis which was new, called the nucleation hypothesis. And this hypothesis was the following. You know, the blue one, the good one, is going to become a bad one. It can be sporadic, it can be spontaneous, or it can be due to some epidemiology, like the mad cow disease, that just eating some cow may give you this disease. It's the process is reversible, and it's reversible up to a certain size. After a certain size, called the nucleus, like let's say size 6, like a polymer or 6 elements, then it becomes stable, and it's only one way, and it's not reversible anymore. And then the disease spreads, and then when it spreads, it can, the polymer lengthen, and it can split. And when it splits, it can split into 2 parts or several parts. And if one part is smaller than the nucleus, it becomes reversible and can come back to a good prion. So we decided to use this nucleation hypothesis in 2003 with Glenn Webb and Meredith Greer to settle down the model. When you have the good one, the good polymer, the good monomers can be attached to a bad one, a bad polymer, which is PRPSC, again for scrappy. So there's a lengthening process, and the bad polymers, they can split in 2 ways, into 2 big parts, large enough, bigger than the nucleation, so the nucleus size, so it's stable. So they are going to give birth to 2 new polymers that are going to lengthen and split again, etc. Or they can give rise to one long polymer and a small polymer, smaller than the nucleus size, and this monomer gives back the monomers to the track, and there the process continues. Each polymers and monomers can be degraded also. So in the model, this gave this kind of equation. If V stands for the monomers, since the monomers don't have like a size for the continuous model because it's very small, it's it's only an ordinary differential equation with this very strange term. So the source term is in green, so it's the cell producing the monomers. Then you have the degradation, and then you have this term, which means that the monomers can attach, this arrow, can attach to the polymers and become and lengthen the monomer. Or you have the splitting rate, and this purple term is due to the fact that a large polymer can split into 2 parts, and one is smaller than the critical size X naught, and then it goes back to monomers. So this plus term is due to this blue term going back to the monomers. And for the polymers, so it's not the equation for the monomers, but for the polymers this time, it's a size structure polymer. And so X is supposed to be the size. And since it's the size, you have like a partial differential equation, and you have like the term of lengthening due to the number of monomers, which is this term. You have the degradation term, and these terms, there are two terms. One is when one big polymer larger than the size X is splitting into size X and the size Y minus X, then you just join the X size in the equation. And when a polymer of size X splits in two, then you lose the polymers of size X, so you have this loss term due to the splitting rate. So this actually, this model was the first of its kind, and it was in 2003. And it was actually a very important work that gave rise to a lot of studies after that. And of course, what we were interested in too was the behavior of the lengthening process of the polymers in the brain. And so we started some numerical simulations when you can see here that when you start the initial condition, time is here, and I can move the arrow if you want to, so that you can see the initial condition. The time is in days. It's two. Okay, hold on, because it's not supposed to be up. It's supposed to be moving, but I cannot. So this is the starting day here, the starting date, and days are going from 0 to 20. So you see at the beginning of the experiment, it's lengthening a lot, and then it stopped lengthening and it's splitting. And on the y-axis is the size, this axis is the size, and on the z-axis is the number of polymers. And you see the distribution with respect to the size becomes stable, and it becomes stable like most of, like the average size is about like 200. This is the reason is very simple. It's because at the beginning of the experiment, there are a lot of monomers. So the polymers are going to lengthen a lot. Then there are like less and less monomers, free monomers. So since the polymers cannot lengthen anymore, they are going to split. And because they are going to split, the size, average size is decreasing. And after 200 days, it stabilizes to a certain distribution. And actually that's interesting. And we were able to compute that. That is the number of days on the x-axis and the mean length on the y-axis. You can see the mean length is increasing, then reaches a threshold. And because there's no monomers anymore, it splits and keeps splitting. And it does not go to 0. Like the mean length goes to an average of, let's say, 200. So that gives us some hint about the fact that there were like several equilibria, and we prospected it analytically. So integrating with respect to the size, we ended up with a system of 3 equations. V is still the monomers, U is the total number of polymers of each sizes, and P is actually the mass of each polymers. That is the total number of monomers in the polymers. So it's the mass. You can consider this as the mass of the polymers. And what happens is the following. We found with this system 2 steady states. One called the disease-free steady states because there are no mass of the polymers, of course, so only monomers. So it's called the disease-free steady state. And we found there was also a disease steady state. That is when it's fatal for human, that is the disease settles down and it's stable and the patient is going to die. So the question was like, what would be the parameters that makes the disease steady state stable? And actually, that was the condition we found. And this condition, I will show you here. The disease-free steady state is stable when you have this kind of condition. We can consider this condition as the R0 for the epidemiology. So if you divide by beta x0 plus mu, then the R0 is less than 1, and then you get the disease-free steady state stable. And if you get the exact opposite, that is this one, term is greater than this one, that is, if you divide by this term, then the R0 is greater than 1, then you get the disease steady state. And we proved that under each condition, each disease-free or disease steady states could be globally asymptotically stable with the Lyapunov functional. So that was an interesting work, and that was the first time that we investigated the fact that an epidemic, I mean a disease like the prion, could settle down depending on some very simple parameters for a model. So we worked on this, it was almost 20 years ago, and we did a lot of experiments, a lot of other models, up to very recently, where a researcher came to us and told us that it's a little bit more complex than that. And actually, Mustafa Adimy joined this problem with me, and the discussion and the model. And the problem is that if you see this neuron here, and is producing monomers, and the monomers are giving birth to these polymers, and the polymers are around the neuron. When the neuron is surrounded by polymers, then it's going to be so stressed that it is going to stop producing anything, and is not going to produce the good prion anymore. And since the polymers around the neurons can just move around, and they are going to diffuse into the brain, they are going to go away from the neuron. And when the environment of the neuron is becoming safer, the neuron becomes okay and not stressed anymore, and is going to produce prion again. So you get this kind of phases where the neuron is going to produce prion, which is going to become bad prion. Then if there's too many bad prion, the neuron is stressed, is not going to produce the good prion anymore, and until the bad prion just disappears from the environment, and then it comes back to producing the prion, etc. So it's kind of a process that is very interesting, and we decided to start a modeling of that. And this process is called the unfolded protein response. Just we started with only one neuron, and I will explain you why after. If you say that a neuron is this part, like this yellow part, it's a neuron, and on the surface you have the blue good prion produced. Then you have the bad, the pathological prion around, and they are going to polymerize, and they are going to catch the good prion from the neuron and increase it. But what happens, like if the red is too numerous around the neuron, I told you the neuron is going to be so stressed, is going to stop doing anything. So that's the next slide. So if there are too many accumulation of polymers, then the unfolded protein response stresses the neuron. That is going to shut down the production of prion. That is going to let the time for this protein, the red one, to disappear, being degraded or diffused. And then once this surrounding is clear, then the message is like, you can stop being stressed and you're going to produce good prion again. So how do we model this with a simple mathematical approach? Let's say you've got this first squared called the neuron, and it takes a times capital T for a neuron to detect that there's no stress and to produce the prion, then to attach the prion at the surface. So this X here is the number of monomers attached to the cell surface. And then they just, when they are in contact of the bad prion, they are going to move to the extracellular neuron. That is, it's detaching from the neuron and go to the environment. But if there are like too many PRPSC, that is too many bad prion, then you have a feedback control, and then it's going to be stopping the neuron because it's stressed, and the K of U of T, capital T, is going to stop, etc. So this gives, for the equation of X and Y, something very similar. You have like capital A of T is U of T, capital T, is this function of T here. For simplification, we call it capital A. You have the degradation, mu and alpha, and you have like the process where the rate at which monomers are attaching the bad prion and go to the red compartment is here. They are coming to the red compartment, and you have like a death degradation rate here for alpha. So that's for the blue and the red compartment. For the black compartment, the neuron, it's depending on age, and it's very simple partial differential equation. So that means that the process of going from the entrance here to here, it's straightforward. There's no degradation. It's just the process of producing a prion. What is interesting is the feedback control. It's a Hill-like function. That is, if there are like not so many red polymers, which is this part here, then you get the maximum rate of control here. There's no problem. Like you can produce a lot of PRPSC. If there are like too many PRPSC, then the production, like the signal, the U of T 0, becomes almost equal to 0. So you stop the production of protein, but it takes a time T to realize that. So it's not straightforward. So that's the reason why, if we just skip this one and consider only these two compartments, it's possible, because this is only a compartment when it's the production of good prion, and you end up with a delay differential equation where you have like the X, the cell surface prion, depends on exactly the situation of the total number of bad prion at time T minus minus capital T, and the rest is about the same. And this is what we decided to investigate. And what happens? It was possible to show that only for one neuron, you can get a disease-free steady state. That is, you are not going to produce enough bad prion for the prion to stress the neuron, and it's possible to survive, and the neuron is going to not to be stressed and keep on producing good prion. And under some condition, you get the disease-free steady state unstable, and the endemic, which is going to be stable. And you can see it depends on alpha, which is the number of diffusion. Let's say that alpha is degradation and also diffusion, like it's clearing the environment of the neuron. And so you can get both depending on these 4 parameters, and you have like very close to epidemiological model, but inside a neuron, inside a cell model with a neuron and prion. It's possible to show that we get some oscillations, because with the differential equations, it's very likely to get some oscillations, but we proved it was possible with different parameters value, that if you are like with a time capital T of producing the PRPC small enough, you don't have the oscillations. But if the time capital T for a neuron to produce the PRPC is too big, then you get some oscillations. That is, the neuron activity is going to oscillate all the time. And this is going to be very interesting. So we investigated several parameters, and we showed that under some several conditions for some parameters, it's possible to get different type of oscillations. It's always by Hopf bifurcation, but the oscillations depend on the parameters. And so what we did, because it's interesting with one neuron, we decided to see if it's possible to get something similar with several neurons. So we were crazy and took 2 neurons. And what happened is like we decided to have almost the same behavior. Like you have 2 neighbors neurons producing the PRPC, the good one. They are like both surrounded by the bad ones, but they can communicate between each other. So the model is way much more complicated, and it's only for 2 neurons. So imagine. So what is interesting is like the pink arrows, and the pink arrows are the coupling of the 2 neurons. So let's say like if K is equal to 0, we have like 2 independent neurons, and it's like the previous model. Like it's not very interesting because we did the study. What is interesting is like when K is different from 0, and we ended up with some steady states. And what is interesting is like we had a condition of stability of the disease-free steady state. That is, you don't produce, like you are not like the polymers, the bad prion are not stable. Not only if each are not of each independently neuron is less than 1, but also with the condition. That means, and this is maybe one of the most interesting part of this problem, is that if we have like each neuron independently showing R naught less than 1, but if the coupling is big enough, then you can get the coexistence of the disease steady state. That is, separately, you like the neurons would not make the bad prion survive in the neighborhood, but if you couple them, well, and if the coupling is big enough, then you can enhance the disease and the stress of the neuron. So I'm not going to go through all the details, but the mathematical analysis was so difficult that we decided to simplify the study in the case where we have like 2 identical neurons with the same rates, like the same production rates, degradation rates, etc., and to get some simpler model and simpler approach. So we got some stability analysis, which was easier to tackle with these simplifications. And what was interesting, I'm not going to go through all that. I will, because I have 3 minutes left. I will show you what we ended up with. It's like when we K, you can okay, I can enhance that. When K, the coupling effect, is becoming big enough, then the zone of the stability becomes not good, like is decreasing for the same capital T, and then you get some half bifurcation and oscillation for lower values of T. And the next one is even better to see. That is like the numerical study of the bifurcation diagrams in that case, where you have 2 neurons coupled together. Is like when the coupling is low enough, you have the trivial equilibrium that is here, that is going to be stable. And then when K is big enough, you have the coexistence of the 2 equilibria, and you can get this half bifurcation occurring, and you have the stress between the 2 that is going to be kind of a cooperative stress. And why do we study this kind of okay, I can finish here. What can we study is the effect on not two neurons, but on a lot of neurons, let's say capital N neurons. So of course, analytically speaking, it's going to be much more difficult, but numerically speaking, it can be very interesting. And the reason why we want to study that is like in the brain, you can have like a large number of neurons in a certain part of the brain that is going to be stressed, so shut down in the brain suddenly for a certain time, capital T. And if this time, capital T, is big enough, you can die because your brain is not going to work for a certain time. And actually, I asked the question about the some clinicians in Lyon, not for prion, but for Alzheimer, which is the process is a little bit similar. And I asked them, do you have some patients sometimes when you dead patients with Alzheimer and you just take the brain and make an analysis of the brain with the sample of the brain? Can you see sometimes like someone dead without any spongiosis, like some plaques or some damages in the brain? And they say yes, and we don't understand why. And that may be a reason why some people can die from prion or neurons without spongiosis all the time. And the question might be very interesting to investigate with some experiments and some clinical data to see that it can be possible to die from prion or Alzheimer without any damages, but just simply because there's a synchronicity of all the neurons that are going to shut down at the same time or not. So that was the purpose of that talk. Is it possible for the neurons to communicate, just to oscillate together with the bifurcation? And the next step is going to get this kind of synchronicity process, and this is what we are going to study in the next in the short-term future. So that's a work that started in 2003 and it's still ongoing. And I'm sorry for getting this small screenshot of my presentation. It was on Keynote, but hopefully it was clear for everyone. And thank you again.
Thank you very much, Laurent, for this nice talk. You have questions or comments? I will check in the chat.
Yes,
yes,
Malé has a question.
Yes, Malé.
Yeah, very nice talk. And as a layman, I just wanted to ask two things. Number one, as you have said that you are planning to do for some sort of synchronization, but at some part this oscillation is not that much observed in real scenario. So I was just thinking that once you are considering a delay parameter, that is t minus capital T1. So before beta n, can we have some exponential negative term, which is a scalar multiple of T1, that there might be a decline in the size of the neuron that might prevent the oscillation?
That's a good question. That's a good question. That's I don't know if the neuron can be if there might be an impact on this decreasing effect.
That actually take care of the fact that within the fixed time period, the expansion or growth of the neuron is not at all of same size. That is not of deterministic size. So if you have some sort of exponential minus delta T1 term, I think Mustafa can understand what I'm talking about. That can actually decrease the oscillatory nature. Because
yes, that would decrease for sure. Yes, that would damp it.
Yeah.
Yes, for sure, that would damp it. But the question is like, the question of this synchronicity does not come from Mustafa and I, the mathematicians, but from the biologist who said that he observed it in vitro, but not in vivo so far. But that's one question that could be very interesting, just to see if in vivo it's possible to get that. And actually, just to see if there's this synchronicity, and if there's a damping term, I guess we won't observe this synchronicity. I mean, maybe we can, but if there's a damping term, I don't think we are going to observe this synchronicity. Mustafa, if you have an opinion on that,
no.
I'm not sure we're going to observe
Yes.
but the damping term, that might be interesting, yes, to investigate.
Yeah,
Yes.
thank you. Thank you. Yeah, thank you.
Another question, I think it's I don't know who. It's Vitaly, maybe? No? Yes.
Yeah. My name is written in Russian, so you may not recognize it.
That's why.
I recognize it.
You recognize it?
Yes.
Okay. Yeah, very good. So, Laurent, a short question. You started from a continuous model. Oh, well, not started, but you at some point you presented continuous model. Can you observe time oscillations in this continuous?
No, not in this. The first model you meant. No, there was no oscillation. We didn't take the delay into account. And actually, that's a good thing that because I forgot to say in my conclusion. It's because we were just interested into the lengthening splitting process for the first one, and I wanted to show how complex it is. And actually, when Mustafa and I decided with the student, we decided to study this problem, we decided totally to elude the size problem because it's very complex. And actually, that's our next step also, to include the size properties and the size structure. But for the first one, we didn't see any oscillation, and actually we were not looking for that. We were just looking for the you see, the disease-free and disease steady state.
I understand. But if you include time delay in that model, in the continuous model,
oh yes, I guess so. Yes. I didn't check actually. That's a good question. I guess we would for sure. Yes.
Okay.
That's a good point.
Yeah. Thanks.
Thank you.
Yeah. Thank you. Any other question? I will check in the chat. No, it's okay.
I can just add something that Vitaly actually is a part of one of the group in my team for studying a spatial process, not for prion but for Alzheimer, which is not too far away from what we do now, but with no synchronicity, but within inflammation process. And Vitaly can tell you that it's a big mess because we decided not to have the continuous model, but the discrete model. It's a big mess.
Well, we'll discuss it next time. Next workshop, we should finish this work.
hopefully. And hopefully it's going to be on live with no problem with my presentation. Hopefully.
Okay. Thank you very much. I think we have 3 minutes before the next.
Was sufficient.
Yes, the next speaker. Maybe Alberto, you can share your screen, and we will start in 3 minutes. But you can start.
Yes, because sometimes it takes more than 3 minutes of time.
Yes.
So
yes.
Thank you.
This is the
Laurent.
screen.
Thank you.
And I maximize. Okay, can you see the first slide?
Yes. Perfect.
Okay, when you tell me, Alberto, start, I will start.
Okay, yes. Maybe I don't know if we have to wait, Vitaly, or we can start. It's
well, you know, people can connect
okay.
for some particular talk. So I think it is better to wait.
Yes.
We have 2 minutes to wait. Yeah.
Very well. I have a question for Laurent. Very short.
Yes.
I'm still here.
Laurent, the material you showed, the last part, did you publish it or is not yet published?
It's submitted. We wait for the answer from the referees. We've submitted it 2 months ago.
Yes.
Yes, but one must be patient.
Okay, but if you're interested, if you're interested,
okay,
I can send
so we'll be published soon. Thank you very much.
Hopefully.
Oh my God.
And by the way, it's nice to see you, Alberto.
Yes, thank you.
I haven't seen you for a long time.
Okay, I think it's time.
Okay.
It's my pleasure to introduce the next speaker. It's Alberto Donofrio from Lyon, and he will talk about mathematical physics of vaccinations. Okay,
Thank you, Mustafa.
You have 30 minutes.
Perfect, perfect. Yes,
Okay.
you stop me in case I am too long. Okay, thank you very much. Oh, so you know, this talk is on a subject that seems a little bit strange. That is the vaccination in case where the disease is absent for the target population. It could seem some very academic topic that I, Vitali, and Antonello Lupic, and Piero, and Professor Palumbo from Messina decided to study just for the pleasure of doing theorems. It's not this case because if you think to poliomyelitis, there is 2-3 countries in the world where there is some sporadic case of poliomyelitis. But it's difficult to convince people to vaccinate against poliomyelitis. In Lyon, when my son was vaccinated, was very happy. The pediatrist of the public system in Lyon, he told me I must struggle to convince people to vaccinate because they say, oh, well, why vaccinate against poliomyelitis? There is no more poliomyelitis near in all the world. And so this is an important topic. And this talk is based on this paper that we published just before the catastrophe, we know very well. And the first author is Antonella Lupica, that then was a PhD student, a great scientist, and also a very hard worker. So which is the key topic of this, the first key topic of this talk, the vaccine hesitancy. All people speaks about now, when you go in the shops, people speaks about vaccines, hesitancy, social distancing, etc., etc. I work on these topics well before, and I had the chance to edit the first book ever published on the role of human behavior and the spread of infectious disease, well before the current pandemics. Okay, so, well, nowadays, in all mathematics faculties around the world, people study this SIR model, and now is also in the news. And the SIR model with mandatory vaccination is very simple. There is an extra term, minus P times mu in the equation for susceptible, where P is constant. This system has a disease-free equilibrium. Lorana speaking of disease-free equilibrium in a totally different context. And there is a threshold by May and Anderson, author of a very famous book that I recently bought after many years because it's out of print now. And their theorem basically say that if the level of vaccination exceed this threshold, the disease-free equilibrium is globally attractive. That is, you eradicate the disease from your population. Also, if there is an importation outbreaks, if the vaccination is continuous, it will be cleared off. But now, since many years, a lot of vaccines are no more mandatory, and also the mandatory vaccine, it's not true that 100% of children are vaccinated against use. So what if P, instead of being constant, is a state variable? This is one of the main topics, modeling P, of the behavioral epidemiology of infectious diseases. In 2005, Bauk with a model, and then take into account some more realistic feature, myself, Miero Manfredi, and Piero Poletti in 2011-12, we proposed a model of P that's based on evolutionary game approach, but we made the error to use the economic approach to evolutionary game theory. I must confess that the economic approach to the evolutionary to the game theory in general, not only the evolutionary one, is one of the most boring things there is in applied mathematics. The payoff, but you must change the scene, something very boring, and people don't understand why there is this equation. It's mysterious. Then I was decided to think an alternative approach leading to the same equation, and we proposed in this book published on Physics Report in 2016 a new approach that is based on a double a process of double infection of ideas. You know, in this is a very simple model where the population of parents, because we are very interested in childhood diseases, but the same applies for other generalistic diseases like COVID, population can be split in two categories, pro-vaccine and against vaccine, or let's say hesitance to vaccine. And they change strategy, and then speaking directly on through internet forum can modify their strategy. Yes, so you have a double process of infection. That is, you have an equation for P and an equation for A, and you see there is this double process of infection of ideas. But there is also an extra term, gamma. This gamma is a term that makes change strategy to people against vaccine. Which is the origin of gamma? The origin of gamma is the action of public health system that in favor of vaccine, that this action has the effect of inducing people to change their strategy. The system in reality can be reduced to one simple differential equation. And these two terms are not constant, but depends on the state of the spread of the disease and the state of vaccination. In particular, MI is an index summarizing the information on the spread of the disease. And MSE is an index summarizing the information of vaccine side effects. It's logic that more information, also fake news, you have on vaccine side effects, the bigger is the force of infection that make you change strategy from pro-vaccine to against the vaccine. On the contrary, if there is very large epidemics, you are pushed to change strategy from anti-vaccine to pro-vaccine. Voila. So two very, very simple example of these two function theta are the most simple one, linear one. This theta mi can be a linear affine function of the prevalence of disease. Whereas the alpha, it can be a linear affine function on the number of vaccine per day, which is, by the way, proportional to the number of side effects, because generally the vast majority of side effects are in few hours after vaccine. Okay. So at the end of history, you have this equation. And you can study and must be coupled with the dynamic of the disease. But what happens if the disease is not present in the population? I is 0. So you have a very simple equation, a differential equation, scalar differential equation, Let's say basically that if there's no state intervention, you have an equilibrium point. Of course, if the force against the vaccine, this parameter alpha, is small, then all people get vaccinated, but it never occurs in the reality. Okay. If gamma is constant, instead you will have an intermediate equilibrium higher than P2 that depends on gamma, of course. But this is a very simple model, no spatial model. So we decided to study the spatial version by taking into account human mobility. And you have practically this couple of equations that can be reduced to a single equation on a set omega with von Neumann boundary condition. Omega, of course, is bounded, but in some case can be considered unbounded. Okay, so you know, vaccine is about prevention. And now a slide about prevention of question. I prevent the following question, but diffusion is not a good model of human mobility. Yes, we know the Brownian diffusion is a very rough, even wrong model of human mobility. And indeed, we are very slowly, because since I'm workless, I'm past the vast majority of my time to finding a new position. We are very slowly working on this, but we will converge to a new model. For example, using super diffusivity, which is a not so bad model of human mobility. Okay, but the true spatiotemporal key point of this work is not searching the best model to model human mobility. This is also important. We are facing it, but is another point. I said that the index M, the two indexes, in this case there is only the second one, are the information on the state of side effect in our case, because we say that in this model there is no, the disease is not present in the target population. And there is a very important point. The information used by people to take vaccine decision and eventually change their strategy can be strictly local. I live in Lyon, I'm all interested in Lyon. Non-local, more realistically, I'm not all interested in the street where I live. And not only in all Lyon, but in all the surrounding area, if not the region. Or even global. One can take decision only based on state level, for example, the whole of omega. This is the model, is that alpha is a linear affine function of two components. The first is a local component, it's every time present, plus a second mysterious component, JP, where I only anticipate that JP is a functional. This functional, that is, JP is the possibly non-local information I use in taking my decision of switching strategy from anti-vaccine to pro-vaccine. And P as a classical form of spatial convolution with a unity kernel. Okay, symmetric also, because there we have no reason, maybe in some special problem can be also asymmetric, but in general is symmetric. And I say, depending on the type of the information that is of the kernel, we can have different. In the first case, if delta is, if the kernel is Dirac's delta, this means that also the second part is strictly local. Okay. Phi can be constant. In this case, JP is nothing else than the average in the set omega of the P, the density of the pro-vaccine, of the which means the density of the vaccine uptake and the density of side effects, of course. Otherwise, phi could be let's say a Gaussian, for example, but even more interesting, because in reality, we are not in quantum mechanics where theoretically an electron in New York can interfere with an electron here on my desktop. Extreme non-locality of quantum mechanics. People do not take into account information, the spread of disease, that is, or in this case, of the side effect that came from a very, very far. They are very interesting in the news around their area. Okay, and so the most realistic kind of kernel is a kernel that is bounded. Bounded in the sense that is on a limited area around the point. So if we analyze the linearized equation, we arrived to an eigenvalue problem that can be stable or unstable, the associated eigenvalues lambda. This depends basically on the Fourier transform of the kernel. Okay, so what happens, or if omega is bounded on the Fourier series of the kernel phi. What happens if, in the most simple case, if the functional is nothing else than the average of p, we have that the equilibrium point remains locally stable because all the eigenvalues are strictly negative. Okay. If phi is a delta of Dirac, is even more simple the case, because the equilibrium point, homogeneous equilibrium point, is not only locally but even globally stable with a very simple energy-like functional. Voila, can be shown by the Lyapunov method. Okay, and the propagation in case of infinite omega is through traveling waves. The most interesting case is when the kernel is non-local but with on a compact set, limited bounded compact set, because in this case P2 can become unstable. That is, the homogeneous solution is not the steady state solution, and is not reached with traveling waves. And this is an example on a bounded set on the onset or a non-uniform steady states. But what is most interesting, if omega is approximately unbounded and the kernel is on a finite limited region, bounded region, around each point, we show a very complex theorem that the solution of system are generalized traveling wave. That is, traveling wave that are not smooth but have a complex behavior rich of oscillation. Voila, this is a simulation corresponding to this kernel. And of course, there is also another kind of non-locality, because people not only use non-local information to take their decision, but they have also a memory, in the sense that they take into account on the past information. In this case, the function alpha is non-local also in time. That is, we take into account of the local information that occurred in the past, and it is doubly non-local information. That is, information on another city, but also not only today, also in the past. So we have a double non-locality that can generate both traveling wave that wildly generalize the traveling wave. Practically here is something that remembers chaotic spatiotemporal chaoticity. Okay. But what about the action of public health system? Of course, the action of the public health system can be easily included, leading to this equation. For our case, where I remember we don't have the disease in the target population, and the system, as we are seeing, is enough complex. Okay. And what is the effect? The effect of the gamma is, of course, we made a series of theorems that if gamma is enough large, practically the sufficient large level in the space of vaccination can be obtained, etc., etc. And this is an example. You see, in this example, we have the double non-locality, temporal non-locality and spatial non-locality, and a gamma that acts from a given instant of time onwards, in the sense that, so in the first phase, up to t equal to 100, as you can see, we have this wild generalizing traveling wave. Then at t equal 100, the density plot maybe is even more clear in the right panel than the normal 3D plot in the left panel. There is a not so small transitory, let's say 20 time unit, where the wild generalized traveling wave is attacked, change shape, and then from 25 onwards, we have a homogeneous level of the density P. So, we are, as I mentioned, working on a more realistic model of human movement, and we are also studying some question of global stability, but with this very important, the case where, much more complex, the disease, the target disease of the vaccine is present in the target population, which leads to an equation much more complex because there is the information that can be not only, let's say, non-local in space on the disprogrammation of disease this time, but also in time. And there is also the model of the spatiotemporal model of the spread of the disease. And this work is in collaboration, we are starting, let's say, with the Malai Banerjee, that is in the audience, Vitali, Professor Vitali Volpert, Antonella Lupic, of course, and Piero, my friend, Piero Manfredi. So that's all. I thank Professor Vitali Volpert for and the other organization organized for inviting me, and that's all.
Thank you very much, Alfredo. Now we can see if there is questions. You can ask questions if you want. I have one question. It's imagine instead of considering space, you consider something like information. How strong is the information? Because now with the internet and with TV, we have more influence about the media that we. Do you think it's possible to do something similar using different kind of?
But yes, here in this model there is the effect of the information. But of course, an important topic, especially to analyze the epidemic in the past, is to model the spread of the information.
Okay. Yes.
for example. Well, in modern time, this is less important because information is now instantaneous.
Yeah.
What you can have is a little bit of delay.
Yes, no, I'm not talking about how strong is the information, because you accumulate some information to take a decision. It's this is what I was thinking. Of course.
Yes, but this is exactly this. The accumulation information to take the decision is exactly this. The non-local, temporal non-locality. This means that people, to take their decision, use all the accumulated information. You can consider here this weight. This is not it's in both time, both at probability density and a weight. In this model, the force that make you change the strategy depends on the accumulation of the past information.
Yes.
Exactly this.
Okay. Yes. Thank you. Vitaly, maybe you have a question?
Yes, I have a difficult question, maybe a little bit philosophical. First of all, I would like to say that indeed it's a very important topic presented by Alberto, because we see during this COVID epidemic how the spread of information and the role of information is different in different countries. And it's even not only the presence of information, but also how we perceive this information, how we react on this information.
But indeed, these terms are perceived information.
Yes, of course. Well, nobody can answer the question, but still we see that, for example, in Portugal, the number of vaccinated people is close to 90%. In France, for example, 75%. In the US, it's 65%. Why it is so different? In Russia, it's 35%. Why it is so different in different?
In different countries, yes. But this is an very important question that is related to the fact that behavioral epidemiology of infectious disease is inherently a multidisciplinary topic.
Yes.
Because this constant, that for us seems apparently mathematical constant, they are very strongly culture dependent. There is in France is very well known that the position of vaccination is much stronger than in all other, I would not say all other, but many other countries. And it's very interesting, this philosophical question. For example, the reason to be vaccinated can be very cultural dependent. I make two examples. Who are in the Western world the most allergic to vaccination for children? There is evidence that are the richest and learned people that are the they have the largest distrust toward the children vaccination. There is studies about, for example, kindergartens in California, where they show that in the kindergarten of rich people, intellectual people working for big universities or the big informatics firms, in that kindergarten, there is less percentage of vaccinated children that in normal people kindergarten, for example. Yeah. This is an interesting. And also the reason to be vaccinated in some culture can be because the head of village said it's very good. For example, in Nigeria, they had a very big problem with vaccine against the poliomyelitis because was a religious and political boss, local boss, that was strongly against vaccine. Then the World Health Organization or the United Nations sent some diplomatic people to speak to them, probably with some, some small luggage.
Yes.
And suddenly he changed the idea.
Okay, yes. I think there is another question from Efim.
Efim Bershatsky. Yes, Efim, go ahead with your question.
Yes, I want to ask my question to Albert.
Hello?
Alberto, do vaccinated people less than mortality in non-vaccinated?
So sorry, unfortunately, the audio is oscillating.
Do you have any direct data that mortality in vaccinated people is less than mortality in non-vaccinated in your country? Or
but yes.
And how much less?
There is a very simple, I can show now. All people can do this experiment. I well understood. So I use Italy, so there is no political problem.
Okay.
You see, okay, we
I'm
are
afraid that
now.
see
This
only
is
your
the mortality.
PowerPoint screen. I'm sorry, Alberto.
Sorry, you see?
I'm afraid that we see only PowerPoint screen.
Oh, okay.
Yeah.
I will change the screen. You have a reason. I understood. I will put the other screen. Which is the other screen? Ah, yes, this one. Okay. So you see, in this period, there was, in these two different periods, there was a lot of cases. There was a lot of cases.
Yes.
The first in this first there was not enough, not yet the vaccine, and here there was the vaccine, and here there was a lot of deaths, and here much less death, because the people with the vaccine have a much smaller probability of get serious form, mortal form of the COVID. This is for COVID. For other diseases, very, very well known. The mortality for hepatitis B of people vaccinated against hepatitis B is ridiculous. And the few people that die because of hepatitis B being vaccinated, if you study them, they have derangement of the immune system or other problems. Okay.
Yes.
People that are not vaccinated have a huge probability to die, much higher than the people that are vaccinated. So, for example, do you know at which age in Vietnam children are vaccinated against hepatitis B? I can tell you, 1 hour of life.
Yes.
Because there is a so large prevalence of hepatitis B, and the childbirth now is in hospital, where the probability to get the disease is huge, everywhere, also in Italy, everywhere in the world, but especially in people in countries with very large prevalence, that children are vaccinated on 1 hour of life, because it's a huge life-changing. In countries with characterized by huge prevalence of hepatitis B, that are not only China, Vietnam, but also, for example, some region of South, and the province of South Italy, including the one where I studied at the time of high school. There was, as a consequence, a very large prevalence of hepatic cancer. Thanks to the masks vaccination, not only hepatitis B has dropped, but even liver cancer after some year. Statistical epidemiologists verified that there is also a drop of liver cancer. And indeed, hepatitis B vaccine is considered as an anti-cancer vaccine. Of course, it's a side effect, but a very positive side effect. The fact is. So this is a very, very, very important point. Thank you for this question.
Yeah. Any other questions?
If I can just,
yes,
just a short.
I don't hear.
Yes, I think
Vital is frozen.
Yes.
Comment concerning the previous question.
Unfortunately,
Bernoulli studied this.
I don't hear.
Now,
Yes,
is it okay?
Yes, it switched too much.
Is it okay now with sound?
Oh, yes, go, please.
Just a short remark that Daniel Bernoulli studied this question in the 18th century. Exactly. About the danger of vaccination and about the danger of no vaccination. And even already at that time, he proved that it is better to be vaccinated.
Yes, it's very fundamental.
And still we continue, and we still continue this discussion.
Yes, because Bernoulli was 200 onwards. Yes, absolutely. And also the first mathematical epidemiology studies by Kermack and McKendry.
Okay.
If you read them, are very interesting, based on very interesting partial differential equation, by the way.
Okay.
Thank you very much.
Thank you, Alberto, for this
Grazie.
nice talk.
Grazie.
Yes, you can, yes. Yes, the next speaker is Daria Neverova from People's Friendship University of Russia. And she will talk about mathematical modeling of immunodominance. Please go ahead.
Thank you. Good afternoon, dear participants.
Yeah.
I would like to present you my talk that is devoted to mathematical.
Please, can you put a full screen? If it's
Oh,
possible?
okay. Yes. 1 moment. Is it okay now?
Yes,
yeah.
perfect.
Okay. So my talk today is about results that were obtained in the frame of joint work by Nikolai Bessonov, Gennady Bocharov, and Vitaly Volpert. This paper is not published yet, but we are preparing it for publishing. So I have planned the following content of this talk. Firstly, I will speak about biological background, where we introduced basic notations and describe biological mechanisms. The second part of this talk is about discrete models of immunodominance. And then we consider continuous model of immune response. Finally, we supplement our continuous model with an equation for virus. So these 4 parts today we are planning to present. Yes, on the slide here you see example of antigen as an influenza virus that has a kind of classic structure. There is some kind of ball with spikes outside, and there is some genetic material inside. Different parts of this antigen that are recognized by immune systems are called epitopes. For this particular example, RNA genome, N and H spikes, envelope, capsid can be these epitopes, or maybe the parts of this part of virus also can be epitopes. Different parts of these antigens can trigger different immune responses by producing immune cells, T cells or B cells. In other words, some antibodies are tuned to red spikes, some to orange spikes that we see here, and maybe some of them can tuned to not only external parts, but tuned to internal epitopes. So in this case, the immunity does not respond to the virus because there is no antibodies tuned to external parts. of this virus. The same situation we have for COVID. So here, this slide is devoted to a brief explanation of interaction between immune cells and antigens. Here, green cells are antigen-presenting cells that capture an epitope, then somehow interact with it, place this antigen on the red MHC-II molecule, and then this structure meets with T cell lymphocyte, T lymphocyte, meets its receptor, and they react with each other. To make this connection possible, T cell receptor and the antigen should match in some sense. It means that there exists some affinity between immune cells and antigens. There are millions of different antigens, and for each of them in our body, there are lymphocyte or receptors tuned to this particular antigen. The similar situation we have also with B lymphocytes. The large orange cells here, this is B lymphocyte with a red receptor to which the yellow antigen is attached. Here, again, some affinity between the receptor and antigen is important. On the other hand, there is an interaction of the helper T cell with MHC-II peptide, where cytokines and interleukins are needed. These mechanisms lead us to the fact that B cells is activated and begins produce the antibodies. So, immunodominance is the immunological phenomenon in which immune responses are mounted against only a few of the antigenic peptides out of the many others that produced. Epitopes to which the immune response is not directed are subdominants, are called subdominants. And the epitopes with the strong response we will call immunodominant. Dominant lymphocytes are activated faster and proliferate more often than subdominant lymphocytes, which are activated later. There will be more dominant lymphocyte in our organism. So for now, the mechanism of immunodominance is poorly understood. So what we know for now about this, that immunodominance is associated with affinity. T cells with greater affinity for an antigen are more likely to become immunodominant. High affinity for T cells antigen contributes to better survival of these cells and their reproduction. Moreover, if subdominant epitope is introduced without a dominant epitope, then the immune response is directed towards to the subdominant one. If a dominant epitope is introduced, the immune response is redirected to that dominant epitope. So we have some switching regimes. Also we have some competition for resources and antigens. And in the long term, it can lead to competitive exclusion of some cell clones or antibodies. It can manifest itself as a gradual decrease of the corresponding cells or antibody concentrations. So now let's talk about discrete models of immunodominance. So let's start with the simplest one model. Here, C subscript I is a concentration of some type of lymphocytes, T T cells or B cells corresponding to some epitope. Under the assumption of sufficiency of resources, the rate of change of concentration is equal to the rate of production of this lymphocyte and the rate of death. So both of these coefficients, we have that they depend on affinity with this index I. So the number of equations corresponds to the number of types of these lymphocytes. We will assume further, for simplicity, that all B subscript I are equal to each other. So, and then we have a more complicated model. You can see it here. Here we consider more model where degeneration term is the same and T cell proliferation is multiplied by the term in the brackets. This term showing the availability of resources. It means that if the cell does not have enough nutrients or some cytokines that it needs to divide, then it should not divide or will divide with a slower rate. So K here, this is all available resources. Resource consumption is proportional to the total. Sorry. Resource consumption is proportional to the total number of cells with the consumption rate Q. And instead of the first equation, we have this one. So, and if we make a bit grouping here and introduce the new coefficient K subscript I, then these equations can be rewrite in this form. Here, coefficient Ki is the following. So consider the simplest case of this system, which has only two equations. We can easily analyze this system and even solve it. In the first case, K1 is approximately equal to K2. That it can be solved analytically in some approximation. And what we have, the straight green line here, this is the line that corresponds to this term equals to 0. All points of this line are stationary points. And also there is another stationary point that is 0, 0. Purple and brown curves here, this is just trajectories of these systems. And starting with different initial values, we will get a different different values of C1 and C2. Each point that we get depends on A1 and A2, and which are associated with the affinity. So this we have that fact that solution depends on affinities and depends on the initial conditions. This fact correlates with experiments that were obtained in this paper that you can see below. So the ratio of affinities and precursor frequencies determine the development of T cell and B cells. Now let's consider another case where K1 is not equal to K2. Then the stationary points will be at the intersection of these green lines with the coordinate axis, and these stationary points are marked as a star. If K1 and K2 differ but not much, then we will have the picture that you can see here. and the beginning of the trajectory will be the same as before. But approaching the green line, the trajectory turns towards to one of the stationary points. So we have that the starting dynamics is the same, but for a long time, one of the lymphocytes completely disappears. This is confirmed by biological data. For details, you can see this paper. So now let's talk about continuous model. A couple words about the derivation of continuous model. Consider our discrete model for many different epitopes. Suppose that they are somehow ordered as real numbers, and we can introduce some continuous variable x. Then, instead of variables with the index I, we get the functions depending on x. So this is the function ax, kx. The sum turns into the integral, and also we introduce some mutations that described by diffusion terms. So we have these kind of equations, and of course, from the mathematical point of view, the questions of the existence of solutions to this equation is always interesting. And it is clear that, of course, this equation has a stationary trivial solution, but what about positive stationary distribution of cells by epitopes, which corresponds to x variable? Is there any positive stationary solution of equation 3 stars? That was the question. It turns out that yes, under certain conditions on the function a and k, there exists a unique positive solution exponentially decaying at the infinity. On this slide, for constant a and smooth function k that presented in the left part of this slide and vanishing in the infinities, we get results of the mathematical modeling of equations that verifying the theorem statement. At the right picture, solution C of x and t is shown at the different moments of time. Here, solution for initial moment of time is the dark blue. This is the stepwise function you can see here. And going from blue to red, we get the graphics of solutions for bigger times. And we get that this solution does not change further from the certain moment of time, and we get the stationary solutions that is red at this picture. So, okay, now a more general question here, and it's how to describe the dynamics of solutions to this equation. When function k is a constant, then there is no positive stationary solutions. There exists a unique stationary solution that is equals to 0. And what happens to the solutions? It turns out that C of x and t converges to 0 everywhere uniformly on the entire axis, but the integral of this solution does not converge to 0. It converges to some positive number. Actually, this number is the value of k, k0. The total number of cells tends to a constant, that's what we have, but the number of cells of each species tends to 0, because we have an infinite number of species. So, and if we imagine that time goes and goes to infinity, then this red line will decrease and we will get some horizontal line or almost horizontal line, which tends to 0 uniformly. Okay, so now we will consider how the number of immune cells for the corresponding epitopes will change in dynamics for linear function k, which is presented here. So the pulse is formed and it moves into the direction of function k increases, and its amplitude grows in a quadratic manner, starting from a certain moment of time. So firstly, it's a little bit decrease. After that, it's increase, but not quadratic, but from certain moment of time, the behavior of amplitude became quadratic. So, and again, we see here the blue one, dark blue, this is the initial condition, and after that, the red one, this is the last moment of time of modeling. So now let us consider the stepwise function k of x that you can see here. For a stepwise function, we can construct an explicit solution that slowly converges to a stationary solution, and this stationary solution is concentrated inside of the step, because here we have that this step function is started from I don't know, 33 till 47, and the same location we have for the stationary solution. Okay. If k of x is a piecewise function again, but with 2 steps, then these steps begin to compete with each other. If we consider 2 steps with different heights but equal width, then stationary solution will be concentrated inside of the step with greater height. You can see it here at the left picture and the same at the right picture. If difference between heights is small, then for getting form of stationary solution, we need just more time. A more interesting case we have where the width and heights of these 2 steps are the same, but different initial functions we have for our equation. So here we obtain different scenarios of distributions of immune cells. It demonstrates the same effect as we get in the case of discrete model for 2 equations where coefficient k1 was equal to k2. So if initial data is the same for both steps, then the stationary solutions, the pulse that concentrated inside each steps will be the same. If we have some disproportion or sum of initial function is bigger or less, then we have exact dependence, the same dependence with the pulses here. But let us know that integral of the solution, which is red one, tends to the same constant for each of these cases. So the last part of this talk is devoted to the model of immunodominance, considering interaction with the virus replication. So the first equation here is similar to the equation considered in the previous section, where we take into account that the rates of cell birth and death can depend on the virus concentration. Indeed, production of antigen-specific T and B lymphocytes is stimulated by the antigens. However, large virus concentration can downregulate cell birth and increase their death rate. These effects are described by this function, phi and psi. Second equation in this model for the virus concentration contains the logistic replication term and virus elimination term. Let us know that the virus concentration depends only on time and not on the space or epitopes variable x. We suppose that there is a single virus variant, but it provides different epitopes described by the continuous variable x with the corresponding immune cells. Virus elimination rate by the immune cells depends on the epitope by means of the function d of y under the integral. In the case where function k and d are constant, here we can obtain the following system of ODE. So denote by capital C the integral of concentration of immune cells and integrate the first equation with respect to x, assuming that the partial derivative of C with respect to x has zero limits at infinity. So we will obtain the system that was studied previously by Professor Volpert and his co-authors. And this system has an unstable node, 0, 0, and some other stationary points depending on the parameters and the function f of v. That is, depends on function phi and psi. You can see it here. Function phi and psi might be considered as a constant function, linear function, sigmoid, or bell-shaped function. And all of this function describes the interact between virus and producing and death of immune cells.
Sorry, you have
yes.
A few minutes.
Yes. Thank you. So, if we talk about stationary solution of this system, so we can get from the second equation the value or how virus can be obtained from it, and after that, substituting this v into the first equation, we get triangle equation. And for this triangle equation, there exists the theorem for which if we put some restrictions on the coefficients of these equations, then there exists positive solution exponentially decaying at infinity. So now I would like to just show some pictures and which describes the behavior of function v. Typical profiles of virus v for different values of parameters has the following form. So there are several scenarios: fast growing, deceleration, slow uniform growth to a stationary solution equal to 1, or for example, fast growing, fast then slow uniform decreasing to a stationary solution 0, and others. But what we have for immune cells here? So if virus is changing with respect to T this way, then the solution, the concentration of immune cells, has this form. So here you can see then when the virus is increasing, then we have situation where integral of solution C of x is decreasing, and at some moment of time it's equal to 0. At this moment, starting from this moment, we have here, and we have the maximum of possible value of virus. After that, these mechanisms trigger the production of immune cells, and we get a pulse that familiar to us from the previous models, previous simulation, which is a very fast amplitude of this pulse is increased. And after that, from some moment of time, it's become growth uniformly and with a quadratic manner. So this difficult behavior and interaction between these two pictures easily to show using this phase portrait, where the horizontal axis corresponds to total number of immune cells, and vertical axis, this is the value of virus. So here T changes from red to blue as a parameter. And this slide demonstrates examples of phase portrait that describes dynamics of solutions to our system that we get. And since this work has not finished for now, it's and I'm not biologist, maybe it's quite difficult for me to give any immunological interpretation. Maybe Professor Volpert will help me with it. So that was last one. Thank you for your attention.
Thank you very much for your nice presentation. Do you have there is questions? Vitaly?
Yes, since you recognize already my name written in Russian.
Yes, I know. I recognize.
Daria, could you please show this system of two equations? Since you asked me to give some biological comments, then yes, this one. Okay, so just a very short comment. Daria is very well explained on that. Just a short biological interpretation or immunological interpretation. So if you see at the system of equations at the left, two equations, one for cells, immune cells, the second one for virus concentration. So there are two functions, k of x and d of y. K of x describe immunodominance. So if k of x, for example, is growing function, then this C immune cells will move, this pulse, this clone of immune cells will move in the directions where K grows, its immunodominance. But the function D of Y, it has another meaning. It's so for example, if you consider antibodies, then what is a neutral? Show the neutralization of antigen by antibodies.
Yes.
So what happens here? K can grow one way, its immunodominance, but D can decrease. So immunodominance does not necessarily correspond to beta neutralizing.
Yes,
this is very important, and this is exactly what happens for COVID-19.
Yes, but yes.
Yes.
Sorry, here you don't consider also the competition between.
No. Well, what Darius wrote in the middle of her talk, it is possible to consider the competition of different clones or antibodies here, right?
Yes.
Unfortunately, we don't have time to discuss in detail now. But what I wanted to comment is that depending on this relation between these two functions, K of X is immunodominance and D of Y is virus neutralization rate. So the outcome of all that. So the final question is whether we will eliminate virus or not. So this is what is important. Yes. But then the answer depends on the relation of these two functions. It can be both. It can be both. It's a complex process. But to make it simple, the relation between these two functions determine whether we can eliminate virus or not. So I will stop on that with my comments.
Okay. Thank you very much. It's, I think, time to move to the other presentation. Thank you for your nice presentation.
Thank you.
The next speaker, I don't know if he.
Yes, it's Kirill Zhudenkov. Yes. He is here. Yes, he is here.
Yes.
Hello, colleagues. Do you hear me?
Yeah. Can you share your screen? Yes.
Yeah, one second. One second. I will try to share my slides. Do you see the slides right now?
Yes. Yes. Perfect.
Okay, that's fine. That's fine.
Okay. Yes, it's my pleasure to present the next speaker. It's Professor Kirill Zhudenkov, and he will talk about modeling continuous longitudinal biomarkers, etc. Thank you.
Thank you very much for the invitation. Actually, my surname is hardly read even in Russian. Mm-hmm. So my Russian colleagues do not always correctly pronounce the surname. It should be Zhudenkov. And I work in the company that is named MNS Decisions. So you see the symbol of the company on the slide. We work in the field of quantitative clinical pharmacology. We work with different organizations, pharmaceutical companies, and biotech companies. And we investigate and solve different problems in quantitative clinical pharmacology in pharmacometrics that incorporates pharmacokinetics and pharmacodynamics, the clinical study assessment and planning, and other things. And this talk is devoted to the modeling of continuous longitudinal biomarkers and events in the analysis and predictions of clinical trial outcomes. On these slides, we will talk about biomarkers and endpoints themselves. Then we overview clinical data that we investigated in this particular example. We will introduce joint modeling methods for biomarkers and clinical endpoints, and we will perform joint model qualification and validation. So the qualification procedure implies the optimization of model parameters against training data set when you have the training data and estimate the parameters against this data and build graphical diagnostics, for example. And the final step of the analysis is the validation of joint models when we utilize the previously qualified models to predict the outcomes of another clinical study. So that's the validation procedure. Let's talk about biomarkers, endpoints, and joint modeling paradigm. As everybody knows, the biomarkers are the measurements that can be performed in clinical studies with respect to different things, depending on nosology, respiratory, oncology, cardiovascular, or any other type of the disease. We can collect different biomarkers that can represent the condition of the patients. So we know that, for example, in respiratory diseases, one of the most important biomarkers is FEV1, which is the forced expiratory volume in 1 second. If we talk about oncology, we primarily talk about the tumor size biomarker that can be measured according to different standards depending on the type of the cancer. And in general, all biomarkers can be split into two large groups. They can be measured at baseline or in longitudinal manner. And these two groups include prognostic biomarkers and predictive biomarkers. If we talk about prognostic biomarkers, they typically indicate the outcome of a patient and can be interconnected with disease severity. If we talk about predictive biomarkers, they describe or provide additional information if a patient can respond to a certain treatment agent. And in case of cancer, for example, the presence of EGFR mutation can be treated as predictive biomarker for a patient. What about endpoints in clinical studies? And actually, talking about biomarkers, I should mention that in early clinical studies, typically concrete values of biomarkers are targeted as an outcome. But if we talk about the late phase clinical studies, they are generally oriented to endpoints. The endpoints represent or characterize the clinical outcome of interest. The endpoints can be objective or subjective. If we talk about objective endpoints, they may be of event type. It can be patient survival. It can be myocardial infarction, stroke, renal failure, whatever else. Also, we can consider subjective endpoints. They can be represented by different symptom scores and other things that are compiled and supported by medical society. So in our research, we do not produce the endpoints. We typically work with the endpoints that are supplied by the customers with their within their clinical data. Also, we can talk about the endpoints that can be called surrogate endpoints. They can be surrogate biomarkers or endpoints. It is a kind of biomarker and endpoint that can be indirectly further used to collect the inference for the true biomarker. And the most popular surrogate biomarkers in oncology, for example, it is the progression-free survival or disease-free survival, while the objective endpoint for cancer studies, it is overall survival. And in many cases, it is quite reasonable because, for example, if we consider early cancers, their survival can be quite high, but we still want to characterize the efficiency of the treatment. That's why a disease-free survival endpoint can be introduced. In our research, we will limit ourselves with a quite small amount of biomarkers and endpoints. We will talk about non-small cell lung cancer investigation, and we will consider just two longitudinal biomarkers that are prognostic biomarkers, the LDH, lactate dehydrogenase, and SLD, which represents the tumor size. We will consider these biomarkers at baseline level and at longitudinal level as well. And generally, if we want to describe the appearance of the biomarkers from a clinical study, we can draw the figures like the ones on the left. So the upper left figure is a typical description of longitudinal trends of tumor size in centimeters. And if we want to describe the endpoint of overall survival, we can draw the Kaplan-Meier estimate and in this way build the curve. So it is a very convenient way to non-parametrically provide the inference on patient survival or whatever other event considered in the study. If you are occasionally interested in endpoints and biomarkers and joint modeling of these endpoints and biomarkers in other diseases or nosologies, you can pick few examples from respiratory medicine, nephrology, and other diseases that are provided in the table here. And in the bottom of the slide, you can also check the publications of our group. The first publication is dedicated to the chronic obstructive pulmonary disease, when we investigated the interconnection between FEV1 and patient exacerbations. And the second work is also dedicated to similar disease, non-small cell lung cancer, but we investigated the interconnection of tumor size and overall survival in a bit different technical manner. What about the joint modeling workflow? What should we do when we want to assess both longitudinal biomarkers and event data in a clinical study? In this presentation, we propose a workflow that incorporates different stages of the analysis, and it can be split into 3 columns. The first is dedicated to the data exploration, the second is the qualification of the model, and the third is the validation of the model. And on these slides together, we will see how we can go through this workflow and what information we can acquire from the data. What data have we collected for the investigation? We accessed the international repository of the clinical data that can be used for different kinds of your own investigation. The repository is called Project Datasphere. You can register at this website and get access to the data for your own research. And for our own research, we collected the data from the 2 clinical studies. The training data set was comprised of the data with docetaxel treatment of advanced and metastatic non-small cell lung cancer. And the second data set included the information for the patients that were treated with a different medicine. Erlotinib, it is a targeted therapy. And actually, you may ask, how could we use one data set as training and another data set as validation, since we are dealing with different treatments with different drugs? And the answer will be that the nature of the biomarkers that we are investigating, the tumor size and LDH, they are prognostic biomarkers, so they can be utilized to assess the study outcomes regardless of treatment type. We want to build the graphical diagnostics of the biomarkers, so we can build the plots like you see here. So the tumor size plots are located on the left part of the slide. The LDH evolution in time is plotted in the middle of the slide. And the Kaplan-Meier estimates from the overall survival data are located on the right part of the slide. When you overview these plots, you can spot an interesting thing. The Kaplan-Meier estimates say to us that patients die from time to time. So the survival is not constant, it goes down. And the biomarker trends suggest that the overall or averaged trend does not go seriously down. It looks a bit strange. And the reason for that is that is due to the patient dropout from the study. The lower tumor size the patient has, the longer the patient can stay in the study. That's why the patients for which tumor size grows pretty fast, they leave the study, unfortunately, they die. And the patients with smaller tumor sizes can stay for a longer time. That's why we can observe this a bit strange average shape of the tumor size, because everybody knows that in general, if patient has a cancer, it unfortunately tends to grow in tumor size. How can we utilize the joint modeling technique to integrate the data of tumor size, LDH, or any other biomarker of interest and overall survival data? Joint modeling is a statistical technique that can incorporate different submodels together. First type of submodels that should be incorporated in a joint model is called the longitudinal submodel. Generally, for the longitudinal submodels, mixed effects models are used. They can be of two groups. It can be either linear models or non-linear models. If we talk about linear models, they are typically presented by lines, polynomials, or splines. And if we have a complicated, complex shape of the longitudinal biomarker curve, natural splines can be quite good to describe this complex shape. That's fine. However, if we want to introduce some mechanistic behavior, or at least empirical behavior of the curve, we should use non-linear models that are presented on the right. So these models can be formulated in terms of, for example, explicit functions. In our case, we utilized the empirical bi-exponential model that can be, if you wish to investigate different empirical models for tumor size description, you can overview one of the links to the publications that are supplied on the bottom of the slide. Also, if you want to build a mechanistic model, in nonlinear models, you are capable to utilize, for example, the ordinary differential equations to describe your biomarkers and system components that lead to biomarker composition. So, for example, when we listen to the previous discussions and previous slides, we talked about the immune system response and other things, and the components and dynamics of the components of immune system can be utilized to incorporate a more complex, which is typically called systems pharmacology model of immune response that finally estimates or predicts the tumor size. So even these advanced systems pharmacology models can be used as a longitudinal submodel for biomarkers. What should we say about time to event data? I'm sure that most participants of the conference are familiar with basic time to event models, and a time to event model can be formulated in terms of probability of event to occur at certain moment in time. So it's the upper formula on the slide. It is called hazard function. Having formulated the hazard function, we can integrate it to a needed extent to acquire survival probability. It is the individual survival probability for every subject that we are considering in the study. When we want to assess the marginal survival probability, we can average these curves, and this averaged curve can be compared to the Kaplan-Meier estimate that is plotted on the right of the slide. And of course, those who dealt with time-to-event models, I'm sure they are familiar with the proportional hazards models, the hazard function of which is presented at the bottom part of the slide, bottom left part. So it is composed of the multiplication of the baseline hazard function, which is h0 from t, and the exponent under which we see the sum of the covariate effects, different covariate effects with their coefficients. So the covariates can be the tumor size, the neutrophil levels, the LDH, the WHO patient score that represents the condition of the patients, and smoking status, for example, as well. So here, all components are integrated in the proportional hazards submodel. If we stay within Cox proportional hazards models, if we do not go into joint modeling and we are interested only in baseline covariate levels, we can even not specify the h0 from t, the baseline hazard. In case we are working with joint models, we need to specify this hazard in either way. For example, we can have the Weibull formulation of baseline hazard, or spline formulation, or piecewise constant. In our case, in our research, we used Weibull formulation. And if we want to estimate the parameters of longitudinal submodel and time-to-event submodel jointly, we should compose the logarithmic likelihood function that is represented by the formula in the middle of the slide. So you see that it is quite a compact shape of the formula. Generally, the sense of the formula represents the probability that with given model parameters and given time to event submodel components, your model is capable to represent both the longitudinal biomarker and time to event data. And the principle of maximum likelihood moves you towards the estimation of optimal model parameters. And the way to maximize this function can be different, and it is highly dependent on the software you have chosen. Actually, you can use different types of software that is capable to work with joint models. In our example, we utilized just 3 examples of this software, and the actual list of available software is even more exhaustive. However, we picked 2 popular types. We picked JM or JM bias package, which are fully based in R statistical environment, and compared it to Monolix software, which can also be controlled from R environment. However, it has the graphical user interface and may be very convenient for non-experienced user who wants to get acquainted with quantitative clinical pharmacology. And JM and JM bias package are capable to handle linear models only, so linear submodels of longitudinal biomarkers are available only. In Monolix, you can play with nonlinear models with explicit functions with ordinary differential equations as well. Before we got down to the joint models, we performed quite a simple investigation. If you do not want to spend your time to the analysis of longitudinal trends and other things, and just want to stratify what combination of just baseline biomarkers can be optimal for your research, you can use standard functions in R from the package that is called survival. It is Cox PH function. it can help you to estimate, to optimize the parameters of Cox proportional hazards model for baseline biomarkers only against time to event data. So you do not describe longitudinal biomarkers with these models. However, you can stratify the importance of baseline biomarkers. And in this case, we tested just 3 models: the univariate tumor size SLD model, univariate LDH model versus multivariate SLD and LDH model. And we can stratify these models using different criteria. And one of the criteria is the archaic information criteria, and the lower the criteria is, the better. That's why the optimal model from the list of Cox models is the multivariate model when we utilize baseline SLD as tumor size and baseline LDH. Then we decided to investigate what impact of longitudinal biomarkers and is available for us and what it can provide us with. If we talk about the workflow that we presented, we of course estimate the parameter values against the training data set, and more interestingly, we built the graphical diagnostics of the model that is located in the middle part of the table, in the middle of the slide. So we built the visual predictive check plots for longitudinal biomarkers and survival goodness of fit plots when we overlay the average survival curve for individual survival probabilities that are acquired in the model against the time to event data that is plotted in terms of Kaplan-Meier estimates. When we qualify the model, we acquire the parameters, and interestingly, we collect a fine goodness of fit plots in this model. So here in black color, the data in these quantiles are plotted. So the mean quantile of the data is the average. And we see that the model can describe the data very well in terms of longitudinal biomarker trends. It can describe well both SLD tumor size and LDH. The model is also capable to track the survival curve well as well. And then when we build the nonlinear model, it also has quite high performance in terms of graphical diagnostics. If we switch slides forth and back, they represent more or less similar performance of the models. And keeping in mind that there is a crucial difference in model structure, because the linear models are compiled in GM package and non-linear models are generated in Monolix. Let's see whether there is any difference in model performance when we try to estimate, to predict and assess the quality of prediction of longitudinal biomarker trends and survival against external data, which was not initially used to build the models. That, just to remind you, it is the second study that is presented with the treatment with erlotinib. So let's go to the validation procedure. In terms of validation procedure, we didn't only build the visual predictive check plots for longitudinal biomarker trends and survival curves. We also introduced the discrimination analysis that implies the calculation of time-dependent receiver operation characteristic curve, AUC, and Breyer score. In very general words, it means how well the model is capable to differentiate survived patients from non-survived patients. Because if model is not capable to differentiate well, it can simply mix up the outcomes of the patients, and at average, the outcome will be fine. But all patients can be mixed up. And the higher the ROC AUC and the lower the Breyer score, the better the model performance in terms of patient discrimination. And generally from these plots, we see that the multivariate joint models, both linear and non-linear, have the highest performance across the univariate models. And they provide much higher performance than Cox proportional hazards models that utilizes baseline biomarkers only. However, the top performance is achieved by the non-linear model that is created in monoliths. And this effect, to some extent, is represented also on the level of graphical diagnostics of the model. When we build the visual predictive check plots for longitudinal biomarkers, for linear joint models, which are located on the left part of the slide, we see that even the central quartile trends for the model and the data do not coincide pretty well starting from the 6 months of the data prediction. Actually, the validation procedure is a bit complex here because when we validate the model against external data, we supply the model with a limited amount of data from external data set. Approximately 3 months of longitudinal information is collected. And having inferenced with this information, the model is capable then to predict the further outcomes, as if we collected interim data for a new clinical study and want to predict what it ends with. And we see that in this case, if we use just linear models, we are not capable to fairly well predict the longitudinal trends. However, the survival curve is predicted more or less well. But if we utilize non-linear models, the quality of our predictions goes much, much better. And it is plotted in the middle part of the slide for non-linear joint models. That's how we can utilize the longitudinal information from biomarkers and patient survival data in non-small cell lung cancer and analyze the impact in interconnection of tumor size, SLD, LDH, and overall survival, and predict the study outcomes. So the workflow that we presented here incorporates the data exploration and the initial assessment of biomarker importance, joint model building and qualification against a training data set. Also, we can build linear and non-linear submodels for longitudinal biomarkers and predict the study outcomes for external data. And to our view, the joint modeling is a new statistical methodology that can become more and more useful when we integrate the data from the growing amount of new clinical studies, early clinical studies, late clinical studies. When we utilize prognostic biomarkers, we get the capability to predict the study outcomes regardless of treatment type. Of course, these approaches have a set of limitations, and that can be found at different points depending on your concrete project. However, in general, in oncology and in many other nosologies, we can gain much from joint modeling. So I suggest you to investigate this methodology and utilize if you got interested in quantitative clinical pharmacology and clinical study outcome analysis. Thank you.
Thank you very much for your nice talk. We have 3 minutes for questions. Yes, Vitaly?
Yes, thank you very much for the presentation. And of course, this is a very important question about biomarkers and their prognostic values. But I think that this is what is the most difficult is to find appropriate biomarkers. So in your work, do you use some known biomarkers, or you try to develop to find something new?
Thank you very much for this interesting question. Actually, the clinical study and investigation history is quite rich to the moment. That's why for different diseases, we have many established prognostic and predictive biomarkers, but not all of them are assessed for the importance in longitudinal manner. So typically, they are investigated at baseline only, but our ability to predict the study outcomes is limited then. So this joint modeling can bring us towards more efficient study outcome prediction. Also, as you say, if you collect the new clinical study data with the new biomarkers measurement, for example, circulating tumor DNA, perhaps you have already heard about this biomarker. For certain cancers, it becomes a new standard to use this biomarker to describe the study outcomes. So in certain cases, we can explore new biomarkers or their combinations. And then we even talk about hierarchical joint models. So when you compose different items that together affect your endpoint, that's also possible.
Yes, but okay, thank you. I understand what you say, but exactly about what you presented, tumor size as a biomarker. This is probably something I missed something because, well, rather often it's metastases which are considered as the most life-threatening, well, cancer development, and maybe not exactly tumor size. Moreover, for large tumors, there's also surgery which often applied. So between surgery and metastasis and for other factors, is really tumor size is a real crucial, the most deterministic biomarker.
Quite an interesting talk. Thank you very much. It is true. Yes, you are completely right. If we collect any non-small cell lung cancer patient with different stages, from stage 1 to stage 4, the tumor size may become not the most important biomarker. For stage 4, it can be the occurrence of metastasis and other things. Yes, it is. But when we talk about the clinical study data, when particular patients are included only with stage 3B and 4, they all have metastasis typically. And the key difference between these patients is the tumor size. In some cases, you can also introduce additional baseline covariates. For example, the existence of metastasis in brain. And it can be important, yes. In this research, we do not introduce these things. However, we used the well-established biomarkers of SLD and LDH. LDH actually represents the intensity of decay processes associated with cancerogenesis in these patients.
Thank you.
Thank you.
Thank you very much for your. Any other questions? No. Thank you again, and I think.
Thank you, colleagues.
Yes, we can. Vitaly, you can.
Yes,
share your screen.
Yeah. At least I will try.
Yes.
I had some problem, but okay. Let's see how it works.
Yes.
Do you see my? Is it
yes,
okay?
Yes, it's okay.
Okay.
Yes.
Then
yes. The last speaker of this session is Vitaly. I think all of us know him, and he will talk about viral infection spreading in cell culture. Thank you. You can.
Okay. Thank you. Yes. Thank you. Hopefully, it will be okay with my connection. Apparently, I'll try to give a short and quite simple talk about on this topic about viral infection spreading in cell culture. And this is quite important because, in fact, all viruses, or maybe almost all viruses, are tested in cell cultures. These are called virus multiplication assays. In this figure, they take a solution containing virus, they dilute it several times, it becomes very, very diluted, and then they put this solution in the petri dish with cell culture. Usually it's one layer of cells, and then you see at the bottom right figure, there are these just white circles. These are viral plaques. So virus infects cells, it replicates inside cells, then it goes out of the cell to the extracellular matrix and infects surrounding cells. And like that, these viral plaques grow. And sometimes these infected cells die after some time. And this is why we see these white circles. These are usually dead cells. So we see that it's a very important for us to understand how it happens and to try to describe it maybe with mathematical models. And what was surprising for me when we started to study this question, that in fact, there are not so many mathematical models devoted to these processes. And in fact, some of them were not very precisely formulated. So we decided to begin with this simple model presented here, and I will shortly explain what is shown here. So U is the number of uninfected cells, then V is virus concentration. So virus infects cells. This is why in the first equation we have this term minus UV. So the rate of infection of uninfected cells is proportional to the product. It's, well, in chemical kinetics, it is called mass action law. So infected cells is the second equation. For infected cells called I here, we have the same production term with the sign plus here. Infected cells can die. This is why we have minus some coefficient I here. Sometimes they die, sometimes not. We'll consider both cases. And finally, the third equation for the virus concentration. Well, virus can diffuse in the extracellular matrix. This is why we have here this diffusion term. Virus is produced by infected cells is the second term, and it is produced with some time delay. This I subscript tau written here, it's time delay in production of virus by the infected cells. And finally, virus can die, and this is the last term. So we will study, we'll consider this quite simple reaction diffusion equations with time delay. So to make this model and its analysis even simpler, let us begin with the case where infected cells do not die. This means that the coefficient beta equals 0. Then these first two equations are basically the same with a different sign here in the production term. We can take a sum of these equations, this production term disappears, and then integrating this equation, we obtain that the sum of two concentrations, uninfected cells and infected cells, is constant. We can express the concentration U here by means of I, substitute in the second equation, and like that we obtain two equations written here. We reduced our system of three equations to the system of two equations. Why it is convenient for us? Because this is what is called monotone reaction diffusion system. I will not go in all details, but what is important for us here to understand is that this is a class of systems for which we can apply different mathematical methods based on the maximum principle, comparisons theorems, and so on. So a very powerful mathematical analysis is applicable to such kind of models. And then if we continue this investigation, and we'll just begin with numerical simulations just to understand what can happen here with such model. So what we observe here, it is shown here in these figures. At the left, it's virus concentration. At the right, it's concentration of infected cells. Each curve corresponds to one fixed moment of time. So if we fix time and we consider virus concentration as a function of the space variable, so we see such a decreasing curve like here. And if we consider this dynamics in time, so it begins at the left, so we have these curves moving like that from the left to the right. You see here consecutive moments of time, the same happening here with infected cells. So this is how this viral infection spreads in cell culture, and this is what we call reaction diffusion waves. So, well, there is a very big theory about reaction diffusion waves. Of course, I will discuss it very shortly now. So we have, this is our model written at the left. Reaction diffusion wave, it's a solution written here at the right. It's a function which depends on the combination of variables x minus ct. C is the wave speed. This is an unknown constant. This is what is important to keep in mind. This speed is unknown constant, and we should find it as a solution of the problem. But if we substitute this solution in our equation, in our system of equations, then we obtain this ordinary differential systems of equations. The first equation of the first order, the second equation of the second order. C here unknown constant, the wave speed, and because of time delay, we have also here this W depend on the space variable plus C tau. It's because of time delay. So it's not a usual just reaction diffusion system, not the usual ordinary differential system of equations. It's a little bit more complex, but all this mathematical method I mentioned before can be applied to study them. Of course, I will not stop on this today, very briefly. But from the point of view of applications, in particular this viral infection, what is important for us is the speed of this wave. The speed of this wave shows how fast this viral infection will spread in the cell culture, and this is also related to virus virulence. This is also important already, not of course only for cell culture, but for this infection spread in the population. There are some methods which allow us to determine the wave speed, and in particular this method which we use here is quite simple. It is called on the linearization of the problem. Of course, I cannot stop on that. Now, people who are familiar with this theory will easily recognize we linearize the system, we look for eigenvalues and so on. And this quite well-known method allows us to find explicitly the wave speed. In fact, what we should know here and recall that this is not a single wave, but there are many waves with different speeds, and we are interested in this minimal speed, and we obtain this explicit formula for the minimal speed, which is written here, and then we compare, for example, with numerical simulations, and we obtain an exact correspondence. So the next step, it will be, this one is the only mathematical slide in this presentation, of course, without any details, but of course, studying all these questions with our mathematical background, we are interested in some mathematical questions, and the questions of wave existence, it's among such questions. Usually it's a quite complex question. Here we can prove the existence of such waves for all speeds greater or equal to the minimal speed, but we should not forget that this is a problem with time delay, and time delay usually greatly complicates all these mathematical investigations. And here we obtain this existence results is obtained under some additional conditions on this time delay. It should not be too large. And I think this is not only a technical problem, because it is possible that for large time delays, the spectrum of the problem, just a couple of mathematical sentences, the spectrum of moreover, the essential spectrum of the problem can cross the imaginary axis. It becomes a little bit more delicate. But that's all for mathematics. Let's go further. And then if we do numerical simulations for this second case where beta is positive, so the idea is the same. We still have this wave propagation, just a little bit different, because this profile of virus concentration is now different. It's not monotonic as a function of x. It's a pulse shown here, and it propagates like that in space. And here is shown the dynamics with some just decaying oscillations. But what is important here, we can find from these simulations the total viral load in the cell culture. So from the modeling point of view, we just take the integral of this function. We have this function v of x and t. We integrate it with respect to x, and we obtain this integral as a function of time. So it's total viral load as a function of time. And here this graph at the bottom shows how this function, total viral load, is a function of time. So the horizontal axis is time, the vertical axis is total viral load in the logarithmic coordinates. And this is what I will discuss a little bit in detail, because this is exactly what is measured in the experiments. So for all these viruses, in particular for this new coronavirus and for the old coronavirus, they do these experiments. In particular here, it's a culture of epithelial cells. This shown in red here, these are infected cells. And this area of infected cells spreads in the culture. And then they measure the total viral concentration. And they obtain experimentally the curves shown in this right figure. There are several curves. There are some details. I will not stop on them now. But the typical form of this function shown here in logarithmic coordinates. So first it decreases, then it increases quite fast, and then slower. So this is what we will try to model now. So if we apply now the model which I showed you before, the three reaction diffusion equations, and if we find this total virus concentration, this integral, so just we compare with the experimental data, and we see this red dots, these are experiments, and this blue curve, these are simulations. Well, there are some details, can be a little bit different at the left and the right. It's a little bit different. I will not stop on that. So, and in fact, of course, we have to fit parameters, but there are only a few parameters here. This is what is one of the interests of this quite simple model, only a few parameters. And these parameters we can quite precisely determine from the experimental data. In particular, time delay here, we see that, for example, in this experiment, time delay is about 2 hours. In this experiment, it's about 10 hours. So we determine these few parameters, and we obtain a good fitting with the experimental data. And then if we analyze this experimental data and also the simulations, we see that, in fact, there are clearly 3 stages of infection progression in cell culture. So let us look at these red dots or on the blue curve. So in the beginning, we see that it decays. Then there is a very, very strong explosive growth, and then it is constant here or almost constant here. So what happens here? Why we have this delay here? Obviously, because virus takes some time to begin to replicate. In the beginning, it's already present in cell culture. We introduce it, but it does not immediately replicate. It takes here 2 hours, or at the right 10 hours. during this time, virus concentration decays exponentially. It's an logarithmic coordinates. And then after this time delay, all these infected cells begin to reproduce virus, and this is why we have this explosive growth. And after this transient period here, it's about 5 or 6 hours, we observe already this constant or almost constant value. It corresponds to this wave propagation. We have this viral load. You see here, it's kind of a pulse here. If we integrate with respect to x, so we'll have the same value for different times. So this is why it is approximately constant here. Here, in this case, without cell death, it's a little bit different. It's a logarithmic growth here. So this is what we need to understand in this experiment, that there are 3 stages of infection progression, and this is well described by the model. And then, so we discussed previously that this last stage, wave propagation, we can determine the speed of wave propagation. We can determine even this profile. So we can describe theoretically and even analytically this last stage of infection progression. So let us discuss briefly how to describe this first 2 stages. And for that, we do some comparisons and approximations. So here at the right, at the bottom, you see exactly the same model, 3 equations. And at the top, it is the same model, but without diffusion. So just 3 ordinary differential equations with time delay. And we compare them in the beginning of this infection progression. Blue line is with diffusion, red line is without diffusion. So we see that the beginning is exactly the same. After some time, they slightly differ. So looking at that, we can think already that instead of more complex reaction diffusion equations, we can use just ordinary differential equations to describe this beginning of this infection development. But in fact, it can be even simpler than that, because we can even consider linear models. So we have this ordinary differential system of equations with time delay. It contains here this U, the number of uninfected cells, concentration of uninfected cells. Let us replace this concentration of uninfected cells by a constant. What this means is, so in the beginning, we have some concentration of uninfected cells. Let us call it U0. So let us suppose that in the beginning of infection progression, this concentration does not change too much. So this means that instead of U here, we write U0, here U0. So we obtain just a linear ordinary differential system of 2 linear differential equations. And we can solve it analytically, we can solve it numerically. So what we obtain this green line shown here. So in fact, what we see, so that up to time like 4 or even 5, this linear system of equations give a good approximation of solution. If we consider this reaction diffusion system and do the same, we replace U here by U0, we say that the concentration of uninfected cells does not change. We can also solve it. In fact, in this case, we can integrate this equation V, it's a linear equation, we integrate it with respect to X, and we reduce this system exactly to this previous system, we obtain the same result. So what is the conclusion here? In fact, we have this model. This model describes experimental data, and in fact, we can describe analytically or sometimes approximately analytically, all these 3 stages of infectious development. These first 2 stages in the beginning, exponential decay, explosive growth, with just analytical formulas, and here with this analysis of wave propagation. And then it's kind of a basic model. So this is what is important to understand. And then, of course, there are many other different questions and related to that, and I will very briefly discuss some of them. Well, in particular, the model with distributed delay, because not all viruses and cells are the same. So the delay can be not pointwise as before, but distributed. We obtain something close. Another interesting question and important in applications, it's the interferon, because infected cells produce interferon. It's another equation. Interferon down-regulates virus production, but virus can down-regulate interferon production, as it happens, for example, for COVID-19. So this case can be also studied. It's an example of simulations shown here. Two-dimensional simulations, well, rather often it's basically the same than 1D, but when we want to obtain quantitative results, it can be different. In fact, in 2D, the geometry is different. So we have the circular geometry, and so there are more virus produced because of this geometry. Here, if we compare 2D dotted line and 1D, this solid line, so we see that there are more viruses produced in 2D. Well, another interesting question which we study now, I don't have time to stop on it in this presentation, it's virus mutation. Of course, it's very important, we know now, appearance of different variants during this epidemic. So we consider these two viruses. So the second virus is obtained as mutation of the first virus. And using all these previous methods I briefly presented today, we can obtain all this more or less complete description. And what is different with the simpler model with one virus, a priori, we don't know what is the ratio of the two viruses. So the outcome, which of them will win the competition, or maybe they can coexist, and then what is the ratio of their concentrations. And in fact, with these analytical methods, we can give a more or less complete answer to this question. So, well, just some final slides. So there are many other questions which we can and we do study. In particular, I think it was, I don't remember if the first or the second day when Dmitry Grebennikov presented his work on just more detailed virus replication inside cells. It can be included in such kind of models. We can take into account the immune response, and this work, what we do with Christina Leon and Alexei Tokarev. Christina presented it during this workshop. This very complex regulation of immune response, we can bring it together with this model. Of course, it will be much more complex, but the idea is always the same. And in this case, we will obtain virus propagation, not in cell culture, because in cell culture, there's no immune response except for interferon, but infection spreading in the tissue of human organism, together with all these complications related to inflammation, cytokine storm, and so on. So to conclude today's presentation, I would like to say that these experiments and this modeling show, and I think this is what we really need to keep in mind, that there are 3 stages of infection progression in cell culture, and that reaction diffusion equations with time delay provide an appropriate description of this process. And more detailed models, some of them I mentioned right now, with immune response, virus application, and some others, can be included in this basic model as some additional submodels, and this is just some of them. It's works in progress, and some other will be maybe some other questions will be considered later. Thank you very much. I stop on that.
Thank you, Vitaly, for this nice talk. Any questions or comments? Yes. Go ahead. It's yes.
Yeah. Thank you very much, Vitaly, for your very nice and clear, analysis with the, distributed parameter system of the virus, spreading in, cultures. Normally, research just restrict the, focus on, delay differential equations. And my question is the following: in your data assimilation with the time delay PD, did you do the parameter estimation using the data? And the second question is, what was the multiplicity of infection? So what was the initial number of the uninfected target cells and the viral and the infected dose of and the dose of the virus? So
yes, thank you. So yes, we did parameter estimations from this data I showed. We compared with experimental data, and we did some parameter estimations. And since there are only a few parameters, then this estimates, I think, can be quite reasonable. For example, some parameters are easy to estimate, like time delay or diffusion coefficients. They are known. For range for different viruses, and in fact, after that, it remains basically two parameters. One of them is the virus reproduction rate, so trying to keep them in a more or less realistic range from the staying in this range, then we just fix them to the data. And according to your second question, to the initial viral load, for example, yes, we take it again from the experimental data. I will not give you the number like that by head, but we take the initial viral load, for example, from the data.
It just question, maybe you just remember this by heart, whether it was a single round of infection or it was really an infection spreading, where the second case is second scenario is when the viral when the ratio of the virus in the population, or infecting the population is much smaller than the number of the target cells. So whether you have steps here or just a single burst of infection
No, I think it's not a single burst, because what I showed this after this decay phase, there is this large burst indeed, but then it changes to a slow growth.
Okay.
So this slow growth corresponds to the propagation of. But I understand your question. By memory, I just cannot say about the number of cells in this.
Okay. Yes. Thank you.
Well,
thank you very much. Thank you.
I have a question, Vitaly. Yes. What is the impact?
But I completely agree. Yes. Sorry.
Yes. The connection is not good.
The choice of. Is it okay now, the connection?
Yes.
Is it good now?
Yes.
Yes, please. You started to say something, so please.
Yeah. My question is about what is the impact of the delay for the traveling waves? The velocity doesn't depend on the delay.
Well, again, I did not understand completely the question because of some problems with sound, but the impact of time delay is very important because it determines, concerning the wave propagation, because it determines the speed of wave. The speed of the wave depends on the time delay.
You have also the parameter B depends on the delay, no? The parameter, the production of...
No.
Because in general, as there is delay here, this parameter as its production, it has to be depending on the delay, because...
No, in our model, virus production depends on the concentration of infected cells. And here, time delay enters the concentration of cells.
Yes, okay. Any other questions? Okay, I think it's. Thank you very much again, and.
Okay, thank you, and I would like also to thank. Well, now I change from the speaker to the organizer.
Yes.
As an organizer, I would like to thank also our chairman. Recall that tomorrow we have the last day of our workshop, so you are very welcome to come back and to listen to our speakers.
Thank you.
Okay, thanks, and I will see you tomorrow.
Yes, see you tomorrow.